When we think about a covalent bond, the sharing of electrons between two atoms, the simplest approach is to think about one electron belonging to each atom, and in a particular orbital on each atom. The electrons are then shared, the bond is formed, when the orbitals they are in overlap so that the electrons can be close to both nuclei at the same time. The orbitals get filled because now there are two electrons in the space of the overlap. It is in the area of the overlap that the two electrons can exist together and a bond be created. The greater the overlap of the orbitals, the stronger the bond. It is while the electrons are in this overlap region that they are close to both nuclei, and therefore the energy is lowered. The closer the atoms get, the greater the overlap and the lower the energy. However, if the atoms get too close, the repulsions between the nuclei and between the electrons increase faster than the attractions, and the energy rises rapidly. It is the shapes and orientations of the overlaps from the atomic orbitals that give rise to the shapes of the molecules, because the atoms will stay where they have the maximum overlap and the lowest energy. However, it is hard to imagine all the structures we have talked about arising from a spherical s orbital and three mutually perpendicular p orbitals. Where do the shapes we have seen come from? Consider beryllium, whose electron configuration is 1s2, 2s2. Beryllium compounds exist which have two bonds and are linear. We shouldn't even have bonds formed because the 2s valence orbital is filled, and overlap with another orbital with an electron would not be possible, since only two electrons can be in any orbital. There's no room for additional electrons to form the bond. However, if we add enough energy to promote one of the 2s electrons into the 2p subshell, that would allow there to be two bonds formed, and the energy given off by forming two bonds would more than make up for the energy needed to promote the electron into the 2p subshell. But even then, the spherical 2s orbital and the linear 2p orbital seem unlikely to produce a linear structure as we find in the compounds of beryllium. The way we rationalize this is to talk about hybrid orbitals. We take the orbitals we have and mix them together and make new orbitals that are identical. Although you probably are not aware of this, we have already done so. In talking about p orbitals, we talk about the px, py, and pz orbitals, which are identical in shape but pointed along different axes. In reality, only the pz orbital comes out of the mathematics of quantum mechanics with that shape. The px and py orbitals are a combination of the other two orbitals produced so that we have an orbital we can better visualize. In this case, we mix an s orbital and a p orbital and get what we call sp hybrids, because they're made from one s orbital and one p orbital. Unlike the s orbital, the two sp hybrid orbitals have direction, like the p orbital. Unlike the p orbital, the directionality is mostly in a single direction from the nucleus, rather than equally in two directions. In working out the mathematics of these two hybrid orbitals, we find they are oriented 180 degrees apart. This is consistent with the observed structure of beryllium compounds. The new orbital diagram would look like this. In addition to mixing the directionality of the s and p orbitals, creating the hybrids also mixes the energies of the two original orbitals. So the resulting energy is the average of the two. So we would have two sp hybrids of equal energy. This energy is somewhat above the energy of the original s orbital, but below the energy of the two remaining p orbitals. It is important to realize that these hybrid orbitals occur on the beryllium atom, regardless of what it's bonding with. allowing two bonds to form where none would have before allows the energy of the whole system to decrease. Boron tends to form molecules with 3 bonds, so we can mix the s and 2 p orbitals, leaving 1 p orbital unhybridized, to get 3 sp2 hybrid orbitals, which have a trigonal planar shape, 120-degree angles, and energy again between the original s and p orbital energies. This allows the formation of 3 bonds where only 1 could have formed before hybridization. For carbon, mixing the s and all 3 p orbitals results in 4 sp3 hybrid orbitals with a tetrahedral shape, 109.5-degree angles. Again, the energy is in between the s and p energies, and we can form 4 identical bonds. The 4 sp3 hybrids are made from the s and 3 p orbitals. They are pointed towards the corners of a tetrahedron. The black spot is the nucleus of the atom. The large lobe actually contains the nucleus, and the small lobe is usually not drawn. So the combination usually looks like this. To get trigonal bipyramidal and octahedral structures, we mix in 1 or 2 d orbitals to make 5 dsp3 hybrids for the trigonal bipyramidal structure. These are also sometimes called sp3d hybrids, or 6 d2 sp3 hybrids for the octahedral structure, or sp3d2. So we have 5 types of hybrid orbitals: sp, sp2, sp3, dsp3, and d2 sp3, which correspond to the 5 electron domain geometries. This is not a coincidence. The type of hybrid orbitals we have corresponds to the number of electron domains we have around the atom. So, if we have a carbon atom with only 2 domains, as in CO2, we can say with confidence that it is sp hybridized. And a phosphorus atom with 5 domains around it, like PCl5, is sp3d hybridized. Valence bond theory is one of the 2 major ways of dealing with electrons in bonding. It treats the electrons as belonging to the individual atoms with some sharing or overlap producing the bonding. It is relatively simple to think about the molecule as being some sort of mixing of the individual atoms, since we know about the individual atoms and the electrons in them. The other way of thinking about bonding is called molecular orbital theory, in which we think of all the electrons as belonging to the whole molecule and calculate the orbitals for the molecule in the same way we do for an individual atom. Mathematically, this is much more difficult to do, and we will not work with that model in AP Chem. It should come as no surprise that hybridization plays a very important role in valence bond theory. It turns out that there are basically 2 ways orbitals can overlap. This gives rise to 2 types of bonds. The first type of bond is the sigma bond. In sigma bonding, the orbitals are pointed towards each other. This head-to-head overlap is the most overlap that can occur and gives rise to the strongest bonds. The bond is cylindrically symmetric around the internuclear axis. The second type of bonding, pi bonding, occurs in contrast when unhybridized p orbitals are oriented parallel to each other. This side-to-side overlap gives rise to 2 regions of overlap, above and below the plane that contains the nuclei. This overlap is not as extensive as sigma overlap and gives rise to a weaker bond. Whenever we have a single bond, we have a sigma bond. Orbitals will first overlap to produce the strongest attraction. Pi bonds only appear when we have multiple bonding. The first bond of a multiple bond is a sigma bond, and all the others are pi bonds. So a double bond has one sigma bond and one pi bond, and a triple bond has one sigma bond and two pi bonds. Here is an example. In formaldehyde, methanaldehyde, the 3 electron domains tell us we have sp2 hybridized carbon. One of the hybrids overlaps with an sp2 hybrid on the oxygen atom, which also has 3 domains, to form a sigma bond. The other 2 hybrids overlap with hydrogen 1s orbitals to make sigma bonds with the hydrogen atoms. The unhybridized p orbitals on the carbon and the oxygen overlap to form a pi bond. Here is another example. Acetylene, ethine. The 2 carbon atoms are sp hybridized because each has 2 domains. This allows one of the hybrids to overlap and bond with the hydrogen 1s, and the other to overlap with the sp hybrid from the other carbon, forming a sigma bond. The 2 unhybridized p orbitals on each carbon atom overlap and form 2 pi bonds. Understanding and using hybridization helps us understand resonance much more clearly. When we draw Lewis resonance structures for NO3-, it appears that we have multiple bonds that switch around to have the pi bond in different places in the molecule. The reality is different, however. In NO3-, the nitrogen atom and each of the oxygen atoms has an unhybridized p orbital. All 4 of these orbitals overlap at the same time, meaning the electrons are not confined to the area between the nitrogen and one particular oxygen, but are free to move over the whole molecule. This is called a delocalized pi system. Such systems have lower energy. Let's look at benzene as well. Each carbon atom is sp2 hybridized and has 3 sigma bonds to 1 hydrogen atom and 2 carbon atoms, and an unhybridized p orbital. The 6 unhybridized p orbitals all overlap to make a delocalized pi system, which allows the electrons to move freely over the whole molecule and lowers the energy of the system considerably. This makes benzene and other aromatic hydrocarbons very stable molecules. One final point, and this is very important to understand. In order to form a double bond, we must have unhybridized p orbitals. This requires that we have an sp hybrid or an sp2 hybrid. In order to form a triple bond, or 2 double bonds from the same atom, we need sp hybrids. If we have sp3 hybrids, dsp3 hybrids, or d2sp3 hybrids, only single bonds are possible because there are no unhybridized p orbitals.